it's good to have Rajeswari here. She did her PhD from SIMP, and uh, and then since then she worked as a postdoc at uh, IISER Mohali, and then is after that as an Inspire faculty. She's now an Inspire faculty at IISER Bhopal, and today she's going to be telling us about unconventional magnetoresistant behavior in layered magnets.
No,
You are the seminar coordinator. No, you
birds are birds.
have to do all that.
It's a host is fine.
Good afternoon, everyone. First of all, I would like to thank Professor Priya Mahadevan and other faculties at SN Bose for giving me the opportunity to present my work here. And I'm Rajeswari from IISER Bhopal. And today I'm going to talk about unconventional magnetoresistive behavior in layered magnetic materials. So here goes the brief outline of my talk. First, I would like to give a very brief introduction on layered materials, magnetic layered materials, magnetic van der Waals materials, and then I'll present some recent results that we have obtained. In the first part, I'll be talking about van der Waals ferromagnetic material, that is Fe3GeT2, and in the second part of the talk, I'll be talking about magnetoresistive properties that we have observed in a layered antiferromagnetic system, that's PAFE 1.25T3. So one of the class of materials that have come up recently and have become a hot topic in the field of condensed matter physics and material science are the two-dimensional materials. It all started with graphene and then it branched out to several other materials, as you can see over here. So the key feature of these materials are that they are layered materials. They are held in plane with strong covalent bond, whereas the interlayer they are coupled with weak van der Waals forces, and this gives them. I mean, these property makes them easily cleavable down to atomically thin layers and gives us a flexibility in fabricating heterostructures based on these van der Waals materials. And also, like as you can see, there are a wide class of materials, and some of them are metallic, some are semiconducting, some are superconducting, and last but not the least, I mean, we have the magnetic van der Waals materials, the magnetic layer materials. So in this talk, we will be focusing about this magnetic van der Waals materials. Okay, so in the first part of the talk, I'll be talking about one van der Waals ferromagnetic material. But before moving on to the research results, I would like to first start with how it all started. The first experimental evidence of magnetic ordering in our van der Waals layered material was observed in 2017 by scientists from University of Berkeley, California, in this system CR2G2TE6, and that opened up a new horizon in van der Waals magnetism. And as you can see now, we have a wide spectrum of van der Waals magnets. So with this, we are motivated in that although they are, I mean, as you can see over here, there are a number of van der Waals materials which have been theoretically predicted and experimentally observed, but there still remains limited studies available on these materials. So with this, we aimed at synthesizing to look out for new magnetic van der Waals materials. And also, in order to do this, we need to have idea about the already existing van der Waals systems. So we also aimed at synthesizing the known magnetic van der Waals materials, and not only synthesizing, to explore their unexplored properties and also to look out for those magnetic systems which have been theoretically predicted to host non-trivial spin configurations in them. So with this motivation, we started working on one such van der Waals ferromagnetic system, that is Fe3GeT2. Among all the van der Waals materials that has been reported till date, Fe3GeT2 is one such system which has a relatively high Curie temperature compared to the other van der Waals ferromagnets. However, after the discovery of Fe3GeT2, recently there are systems like Fe4, Fe5 which have come up. So Fe3Ge2 is an interesting van der Waals ferromagnetic material which has a relatively high Curie temperature. Okay, and it also has a large magnetic anisotropy that I'll show you in the upcoming results. So moving on to the crystal structure of Fe3Ge2, it consists of Fe3Ge sublayers which are sandwiched between tellurium layers, and there exists a van der Waals gap in between the adjacent tellurium layers. Okay, another feature that makes Fe3Ge2 even more interesting is that it has a simple centrosymmetric crystal structure. However, recent theoretical results have shown that this system can possibly host topological spin textures in them.
So the question, not perpendicular magnetic anisotropy. What does it mean?
Uh,
Perpendicular
okay.
is specific,
It's the out of plane direction.
but anisotropy is with respect to plane to out of plane. Right?
Yes,
So
yes.
how can you define that it's perpendicular?
I'll show like by
This is
perpendicular
anisotropy when you compare between two
two
orientations.
orientations. Yes, and the magnetization value is quite large when the magnetic field is applied in the out of plane direction, and that is what I'm telling
Okay.
it's a perpendicular magnetic anisotropy.
Okay.
So one of the key features, apart from this relatively high Curie temperature compared to other ferromagnetic systems, one of the most important feature of this Fe3Ge2 system is that it has a centrosymmetric crystal structure, and however, from theoretical prediction, it has been shown that this system can possibly host topological spin textures. And also, there was one experimental evidence where people have observed an uncommon behavior in the magnetotransport data when they have measured transverse Hall resistivity as a function of magnetic field. So this makes the system even more interesting. I'll tell you why. Because when I'm talking about topological spin textures here, I'm talking about magnetic scarmions. The scarmions are basically topologically protected spin textures, and their advantage is the atomic scale controllability or the low current induced dynamics. But however, it is not related to my work. So what is important is that the existence of scarmions in a magnetic material can be detected using a simple magnetoresistive technique, that's a topological Hall effect. And what happens is that because of the presence of these scarmions or this kind of textures in the system, the conduction electrons they feel an additional scattering, additional contribution to the transverse Hall resistivity depending on their up and down spin. That's the topological Hall effect. And I'm talking about this because this is what we are going to use in our upcoming results. And moreover, till date, most of the systems, most of the bulk systems where scarmions has been shown to be present are like these systems which are very well known. They have non-centrosymmetric crystal structure. However, and also scarmions can also be observed in thin film heterostructures, but it's very rare. The systems having centrosymmetric crystal structure can host magnetic scarmions in them, and this makes Fe3Ge2 a very hot topic and long sought. I mean, it's a very hot system right now. So with all this motivation, so here we were, first of all, we tried to investigate the existence of such kind of non-trivial spin textures in this Fe3Ge2 system and to understand the underlying interactions, and also whether there is a manifestation of these non-trivial spin textures is being that we can see in the transport measurements, and if we can see any signature whether we can tune that or not. And as we know, one of the simple ways of tuning is via chemical doping. So we also aimed at studying the effect of doping at the magnetic side, that's the iron side, as well as at the non-magnetic side, that's the germanium side. So in the first part of this work, I will be speaking about the effect of doping on the topological magnetoresistive properties when we have doped the iron side, the magnetic side with cobalt. And these are all the systems that I'll be talking about in today's talk. So, okay. So before moving on to any transport measurements, it is very important to have good quality single crystals to perform all these measurements. So we have grown single crystals by the chemical vapor transport method. This is the schematic of the sample growth. You have APGET as the starting element, and in this sample, we have used iodine as the transport agent. And to keep it in the tubular furnace, you have to look out for a proper temperature gradient, and we were successful in getting the single crystals at the pole A after about 2.5 weeks time. Okay. So, and this is one of the image where you can see a quartz tube containing single crystals. And we were successful in growing large single crystals of Fe3GeT2. Okay, moving on to the characterization of the single crystals. Here you can see the X-ray diffraction pattern for Fe3GeT2, hereby I'm calling it FGT, and the two of the doped compounds. And for all the compounds, the XRT pattern that we have observed, these peaks could be identified as 00L Bragg peaks for both FGT and COX FGT, which confirms that the crystal, it basically grows along the C-axis and the exposed plane is the AB plane. Okay? And we have also performed Lave diffraction, which confirms the high quality of the single crystals. And from the structural refinement, we could see that there is an decrement in the lattice parameter C as we were increasing the cobalt concentration.
How did you do that? This is just like that. How can you?
No, we
so
have.
only-
Yes, sir. Well,
so
we
you
actually.
extracted only C parameter.
Yeah.
Fitting it?
No, not from fitting this only. We have powdered.
You powder.
Yeah.
You powder XRD.
Yes. There was little bit problem because in these kind of systems they were
Not easy to powder.
Yes. So we have powdered it for around 2 to 3 days, and then did XRD. And from the rebuild refinement we could get the ABC.
Just by fitting this simulation XRD, because since you have extract C parameter, is it possible by refining?
We can do it using the labels which can give us the profile matching, but then it is better to do the full refinement and extract the values.
Okay.
So
They did not give you ABC, no?
Since she plotted only C parameter.
Only C.
Yeah, that's what only C.
so yes, I have plotted only C just to see that there was the change along the C-axis first.
Yeah, since you want only C,
Yes.
it's been possible just putting this C, but this gives you C. It's okay.
One question I had here is why does it decrease?
Okay. First of all, the size of cobalt, the atomic radii of cobalt is less than the atomic radii of iron. So
It's same valency or you're assuming a different valency?
we are assuming the same valency.
But such a large change because of that. I mean, I don't know. Too large. I thought it's too large a change for just.
In that parameter change.
Yes, parameter change.
It's
The-
0.5% only.
No, it's going all the way. Okay.
Yeah, that's zoomed in change.
No, 16.26 to think, but it
26.
depends on how many layers you have, I guess.
Yeah.
And it is also important to actually estimate the doping concentration in the sample. For that, we could use the energy dispersive X-ray spectroscopy, and from here we could confirm the exact concentration of cobalt that actually was going into the sample.
But why did you dope cobalt?
Yeah. Okay. So
Because there's a report where this Fe5, I think, no? Where you put nickel and the transition temperature increases at 5 or 54.
in case of when we started working on this Fe3GT2, there was no report on these systems, and but that's not the only reason. And when Fe3GT2 has been doped with nickel, it has been seen that it is the magnetization is going down and Ni3GeT2 is absolutely non-magnetic. However, CO3GeT2 is still not stable. I mean,
Not
it's still,
known in
yes,
this
it's still
structure.
not known. So we were motivated. What is happening between iron, nickel, and cobalt is sitting in between. That is one of the reasons. And not only that, our main motive was, I'm saying all this thing, but before doping, we first were interested in actually observing the unconventional transport behavior of Fe3GeTE2. So our first, the gradation of the work was like this. We started with Fe3GeTE2 first, and first we confirmed, yes, we can observe Scarnian kind of spin textures in our system. Okay, first we did that part, entire part was done. Then we started what will happen if we try to tune the iron concentration. So we aimed at, and while tuning, the easiest way is also to look out for the nearest atom. So since we know that
This compound iron itself is like not exactly 3. So this
3
compound
plus and 2
is
plus,
known
yes.
for that now, because you could just without cobalt also you could vary the iron concentration a lot
Yes,
from
yes.
2.8 to 3.2
Mhm.
without putting any cobalt.
Mhm.
So
If
that
not by
also,
controlling.
yeah. So but you can have like if you take extra iron in your CVT, you could
Then
put
yeah,
more
but
if you less.
that is true. Then you have maybe you have to see so many crystals in that and that. So
And
you can collect that series by performing reactions on it.
and also during this process, what I have observed is that even if I take the iron extra during the CVT, it depends on a lot of conditions. Like my crystal growth experience is telling that even if I am taking some extra iron, it doesn't confirm that
It
I
will
am
be
getting the proper concentration, because I have tried on a number of crystals. I have seen
In
it's
CVT, you know how it's going to happen.
that helps
Because it takes atom by atom.
yeah. So if you have more concentration of vapor pressure of iron is more in like iodine.
In more
Right, so it can,
environment. I mean, in
can be
mental
done.
growth, yes, we can understand that there is but in CVT, transport atom by atom.
Yeah, because if you want to make Fe5GT2, obviously you take
six,
5 is to
six,
6.
yes.
You
So
take more
it
iron.
depends how much iron you take. It goes to higher iron.
But in Fe3GT2, I have seen that even if I'm taking 3, it is anyways deficient. But even if I'm taking Fe4, it's still, I'm not being able to control that. For Fe5GT2, I've grown Fe5GT2 also. I can see like if I start with Fe6, probably I'll end up to Fe4.7. But in case of Fe3, I saw
So
that
you have
I'm
more
not being able to
control. You have
control.
more control with cobalt.
Yes. Yes.
That's okay. That's okay. Joining. We have always done that option is
So we have okay. So we have confirmed the concentration of cobalt using the EDX data, and so the takeaway is that we were successful in growing phase pure single crystals of FGP and the cobalt of counterparts. And one study on the EDX mapping from TEM has shown that cobalt actually replaces iron at the transition metal site only. Okay? With this, let's move on to the experimental results of magnetism and magnetotransport that we have done. So moving on to the magnetization measurements, here you can see the temperature dependence of magnetization. From the phi versus V curve, we can see this rate curve corresponds to magnetic susceptibility curve for FGT when the magnetic field is applied along the C-axis of the sample. And this blue corresponds to the configuration where magnetic field is applied perpendicular to the c-axis of the sample. And also, as we are going down from room temperature, we can see there is a upturn over here around 220 Kelvin, which marks the onset of the ferromagnetic behavior. And also, we can see there is a large difference between this red and the blue curve, which indicates there exists magnetic anisotropy in this system. As we were increasing the cobalt doping now, we could see that this PC was getting diminished consistently with increasing cobalt doping. And not only that, the anisotropic anisotropy is also getting diminished with increase of cobalt concentration. Further, we have studied the field dependence of magnetization, and here we have seen that in case of FGT, when the magnetic field is applied parallel to the c-axis of the sample, the image curves saturate at a low magnetic field compared to when the magnetic field is applied perpendicular to the c-axis of the sample. You see the image curves are still not saturating even at a magnetic field of around 6 Tesla, which confirms that the magnetic easy direction is along the c-axis in case of FGT. Okay. So now here you can see the one of the image curves for one of the dope samples, and for all the dope compounds we could see that there is a lowering of the spontaneous magnetic moment with cobalt doping, and also a monotonic weakening of the anisotropic constants with increasing doping. So we calculated the anisotropic constants also are not shown over here. There was a monotonic decrement. And now moving on to the magnetotransport result, the most important result of our work is that here in the figure to the left, it shows you the transverse Hall resistivity when the magnetic field is applied in the z direction, that is along the c-axis of the sample, and we could observe large anomalous Hall effect. And there is one study where they have predicted that this kind of large anomalous Hall effect might arise because of topological nodal line in this material. However, there was no further experimental evidence of this behavior. But what we could see is a large anomalous Hall effect, and the magnitude of the anomalous Hall resistivity decreases consistently with increase of cobalt doping. Now, what is interesting is that when we have measured the transverse Hall resistivity, when the magnetic field is now applied in the plane of the sample in the x direction, okay, so what we have observed is a very striking feature that the transverse Hall resistivity, but first it increases with magnetic field, and it shows a prominent cusp-like feature, and then there is a reduction. And this position of the cusp, it changes with cobalt doping. So this is quite uncommon behavior that we have observed, and that also matches with the first theoretical prediction of possible existence of topological spin textures in Fe3GeT2. Now, in order to probe further, we try to explore why am I calling this an unconventional behavior. Now, if we consider a ferromagnetic system, this convention of this geometry of measurement is nothing but planar Hall measurement. So you can see over here when the magnetic field is applied in the plane of the sample. So when the magnetic field is 0, you have a finite value of Hall resistance, and when I'm increasing the magnetic field, it's continuously decreasing. However, what we have observed is something opposite. It increases, it shows a cusp-like feature, and then decreases. That's why we are calling it an unconventional magnetoresistive behavior, and we studied both concentration dependence as well as temperature dependent study of this transverse Hall resistivity as a function of magnetic field applied in the plane of the sample or perpendicular to the c-axis.
Can you explain that again?
Yes.
What is happening exactly?
Here?
Yeah.
Yes. I'll go back then. Okay. Same figure.
Yeah.
So basically, when the magnetic field was applied in the convention in the z direction, right? And this matches with the c-axis of the crystal. So what we are expecting, what we are observing is a saturation of the Hall resistance, and it has a component from ordinary Hall effect and anomalous Hall effect. Okay. But now, when the magnetic field was rotated and it was applied in the plane of the sample in the x direction, that is perpendicular to the c-axis, ideally what should have happened is that the transverse Hall resistance is supposed to go down, right? But we observe an increment in this value. I mean, it is consistently increasing. It shows a cusp and then it decreases. I'm calling it unconventional Hall effect. I'll tell you that also. Why am I calling it unconventional Hall effect and not topological Hall effect? However, this signature is basically a signature of topological Hall effect only when skyrmions are present in magnetic systems. But I'm not calling it topological. I'll come to the, later on I'll tell that. So what we have
You showed the maybe I'll ask it again. Go ahead.
So what we have done is we have tried to study both the temperature dependence of this, whether this is changing or not, and also the concentration dependence. And from this we have observed this. Now finally our main aim was to find out the different contributions, to separate out the different magneto-resistive contributions using this, and we could find out that, yeah. So what I was telling is this. This is the experimental value that we have observed of the transverse wall resistance. Now, if I extract or if I separate out these two contributions, which goes like this in this case, then we could see that there is an additional contribution to the transverse wall resistivity, which is this one, the full circled one. Okay, and that is observed for Fe3Ge2 and all the dope compounds. We could see that there is a significant additional contribution to the Hall resistivity when the magnetic field is applied perpendicular to the c-axis over the ordinary Hall effect and the anomalous Hall effect contributions, and this might be originating from underlying Skyrmion-like textures in our system. However, we further extended our study and we performed magneto-optical car imaging in collaboration with the Hook University. And what we observed from the MOOC data is that when the magnetic field was applied in this direction, in this direction, okay, we could see some stripe-like domain patterns were coming of alternating contrast, and these stripe-like labyrinthine domain patterns are usually observed in systems having uniaxial magnetic anisotropy. However, what was interesting is that it's very small figure. Like within these stripe-like domain patterns, we could see small bubbles present. Small circular domains, they were embedded inside these stripe-like domain patterns. And that was present for FGT as well as the dope compound. Now, when this magnetic field was changed, it was rotated and it was applied in the plane of this crystal, all these stripe-like domains, they merge together and they form lattice-like structures. And even for a small magnetic field of 20 millitesla, because that's the magnetic field we could access over there. Okay, so we could see that they form lattice kind of structures, and that was present in the dope compounds also. However, the
You
size.
see the pattern even on FG2 with 20 millitesla.
Yes.
But then here, if I see here, the critical field is very high. 20 millitesla.
Yes. Yeah, that's a question that we also have, and that's why I'll tell you, because we didn't. That's the maximum fill that we could give in that setup, and so we could see even at 20 millitesla, we could see those flower-like patterns, and that means that I'm not being able to separate the magnetic domain and the spin textures, right? At such a small magnetic field.
Okay.
I'm talking about this one, right? So that's why, and also because of that only, the size that we got, the size is around 600 nanometers. That's quite large compared to the magnetic Skyrmion size that's known. So that's why we are calling it Skyrmion lattice kind of patterns are happening, but the measurement or the resolution that we had, we could not separate out the domain and the Skyrmion textures.
What do you call it, a lattice? Do you see any periodicity?
Pattern. The pattern is being called as the lattice kind of structures are being made. So that's the reason why am I calling
Normally, skyrmions form
a pattern.
perfect lattice.
Yes.
Could be hexagonally or like
Yes.
kind of.
Yes.
That's not a lattice.
No. Just lattice kind of patterns are being formed, and we could see later on it has been confirmed that it is the basically nothing but Skyrmion textures that are occurring in Fe3Ge2 and the cobalt dope systems, and but the setup that we had, we could go up to only 20 millitesla. So we could not separate out the two contributions, and the size also that we have got is quite large. That's why I'm calling it unconventional Hall effect coming from this kind of textures, but not topological Hall effect.
But in this centrosymmetric system, what do you expect?
Yeah, I'll tell that also. I'll tell that. But however,
But what is your saturation? The magnetization does it show saturation? It is not.
no, it doesn't, sir.
It's not saturated. So
No.
which one is your cobalt group? Okay. So it doesn't saturate, right? So
No.
how do you decouple the anomalous cell part? Because anomalous cell is proportional to M, right?
Mhm.
Saturation magnetization.
Yes.
So you cannot decouple the anomalous cell resistance
You're
from the equation. Yes.
this one, right?
Yes.
So, okay.
You see, just put the
So
value of
just
magnetization there.
okay.
Yeah, this.
So you can do M by H,
Yes.
but you cannot get the rho XY value. Okay, please carry
Yeah,
on.
I've used both the magnetization along that direction and the I mean the Hall data. So,
But your question is right. If she really wants some proper anomalous, then she has to subtract the anti-chromatic component from the total numbers. Then to get anomalous. Actual anomalous. Even in this formula, you have taken M is the function of H or M is a particular value. Like saturation, you have taken the M. Okay. So is it M of function of H, M of H? That's what is question.
yeah, it's a M versus. I've taken the M from the M versus H
H.
cross
So
only.
then
Yes,
it must be function of
yes, yes.
okay.
So, what we have observed is this, but later on from Lawrence TEM, it was shown that yeah, they are magnetic fermions only. And we also tried to do magnetoptical car imaging with a higher magnetic field, and we have sent the samples to IIT Kanpur, but we don't have the data right now. So,
Which group?
Satyajit Banerjee. And okay, so this is the main part of the result that we have observed. Now we finally constructed the phase diagram of the Hall effect versus the doping. So we did a contour map of the magnetic field, the temperature, and the maximum value of the transverse resistivity, additional contribution, the unconventional Hall part, and we could see like there is a significant variation of the unconventional Hall resistivity with increasing cobalt doping, which is,
But why don't you call it a topological Hall?
I can call it a topological Hall. Yes, it's topological Hall effect only, but just that I am not being able to, from the data I had at that time, I could not separate out the Skarmians and the magnetic
But
domain.
you don't need Skarmian
Yeah.
for topological Hall. Topological Hall could be without Skarmian,
Huh.
just by non-coplanar spin
Yes,
texture.
yes.
So
Yeah, I
Skarmian
can.
is not important.
Important. But I can call it topological Hall also, like this. So basically, this hinge was a change in the spin textures with cobalt doping, and this might be because of emergence of some additional interaction that we don't know because we didn't have any probe to investigate that. So we believe that this provides a route towards tuning of the unconventional Hall effect in van der Waals ferromagnetic materials. Now with this, we were interested that I'll move on to the second part here that it was known that in case of Fe3GT2, this kind of systems, the concentration of the iron plays the key role, which
I have
is
one question. This Fe3G2 has three different iron sites.
two.
Two or three?
I
Two
mean,
only, no?
Fe1 and Fe2.
Two.
But Fe1, Fe2 like
So this cobalt prefers which side? Do you have any idea?
yeah, but theoretically it prefers the Fe2 side. However, experimentally it has been observed that it occupies randomly.
Could go.
Yes, it has been observed.
How do you know that
From the EDAX mapping.
Index mapping?
From energy mapping, it has been shown.
How can you tell from energy mapping?
Yeah, TEM.
TM.
Yeah, the energy mapping from the high resolution TEM, they have showed that.
Maybe it's TM, not EDX of TM, but it's
Yeah, the TEM.
Directly
High resolution TEM.
ST scanning.
Yes, the high resolution TEM, where you can see.
The scanning mode.
Yes. It has been, but theoretically it was said like it.
But in that, can you differentiate cobalt and iron?
atomic
it
size.
possible?
They are very close by.
But very close atomic size.
It's very difficult to tell by TEM whether it's iron or coal.
Yeah. Unless maybe there is systematic pattern. The TM only gives the atomic value. Now by finding the pattern.
But where which
But
side
then
it
which
goes?
one
Maybe if she does can you do a Fourier transform and say whether
Yeah,
it's,
it can be.
then you can say whether it's ordered or disordered.
For that, she has to STM, not TM.
You
She
take
has
one.
done mapping. It's not like sector.
And I have not done the TM in my sample, but it has been shown after that the cobalt actually randomly replaces the iron. But it goes to the iron site only. It's not interstitial or anything like that. So,
Reduces the magnetic moment. The transition temperature also decreases and reduces the magnetic moment. Does it bring any fraction or changes the exchange?
So maybe this cobalt compound, if it forms, is completely diamagnetic. Like nickel,
nickel Ni3G2.
completely non-magnetic. Values.
It has been seen in case of nickel doping also that it doesn't obey the Slater-Rowling curve rather than it's basically nickel is kind of non-magnetic in these systems like it happens to be in the nickel telluride cases also. So okay, so we have doped at the magnetic side, but then it is known that in these kind of systems, the iron concentration plays a very key role governing the magnetic properties and all. So we thought like if you do not disturb the iron side and now part of the non-magnetic side, do you even expect to see any changes or not? So with this, we started studying the impact of doping at the non-magnetic side, the germanium side, on the topological magnetoresistive properties in this system. And these are the two concentrations that we have been successful in growing, and we have studied on these two systems only. And what we have observed is that from
So
the
this is the nominal composition which you started with. No? This is not the composition which you ended up.
no, I didn't end up with this one, but there was some problem with the growth.
So this is based on what you start from,
Yes.
and more or less similar you get. as a
Oh,
product.
oh
The
no, no.
composition
Oh,
is what you
I
get.
didn't get your point at that time. This is the actual concentration.
It's so accurate.
Yes.
0.2.
Yes. Like it's not 0.20, it's like 0.19 something. But yes, we could grow after repetitive like trials and errors. But however, I also tried growing higher concentration of arsenic, but I was not successful in growing that.
How did you handle oxygen? Also poison.
Depends on the source.
What is doing
What's your source?
Arsenic metal.
Metal.
Yeah, in powder
Because
form.
in some gaseous form, I think it's possible.
No, if it is cyanide, then it is problematic. Sorry, arsenide, then it is quite
Have you tried ASP?
Mhm.
Have you tried ASP?
Yes, I have recently tried. Very recently. Yes. I don't want to, like, I have not performed any study on that system, so I would not be able to comment right now. Yes, I have grown, but not using this method. So these are the like for the doping part in 83GT2. These are the two concentrations we could grow, and what we observed is that from the temperature dependence of magnetization, this blue curve it corresponds to the FGT when the magnetic field is in the out of plane direction. The blue one corresponds to again to FGT magnetic susceptibility versus temperature curve when the magnetization is when the magnetic field is perpendicular to the z-axis. Same behavior, you see a large difference between the two. But when we are increasing the arsenic concentration, we see a continuous reduction of the TC, and also the anisotropic behavior is also getting diminished with increasing arsenic doping. And moving on to the field dependence of magnetization, um, But we have seen for low arsenic doping that for when the magnetic field is applied along the C-axis, if the image curve saturate at lower magnetic field, and when H is applied perpendicular to the C-axis, it's not saturating at this magnetic field. So it confirms again the magnetic direction is along the C-axis, but however there was a change in case of the higher arsenic concentration sample, where we have observed that there is a weakening of the magnetic anisotropy with arsenic doping, and there is a transition from the out of plane to the in plane direction. And moving on to the magnetic transport result, here also we have observed from the transverse Hall resistivity versus magnetic field along the Z direction, we could see in both the samples a feature of the anomalous Hall effect. However, the magnitude of the anomalous Hall resistivity, it decreases with increasing arsenic doping. And when we have measured the transverse Hall resistivity as a function of magnetic field applied in the plane of the sample, we could see the same behavior of topological Hall effect or unconventional Hall effect in both the systems. And we have tried to separate out the contributions from ordinary Hall effect and anomalous Hall effect, just like the Cobalt doped samples. And we could see here also we can clearly see a significant additional contribution to the transverse Hall resistivity. And so we confirm that this cast-like feature, it passes even for non-magnetic side doping. And finally, we have constructed the phase diagram of the Hall effect versus arsenic doping. And we could see from here you can see that there is a significant variation of unconventional Hall resistivity with increasing arsenic doping. This is remarkable because it indicates a change in the underlying topological spin structures by perturbing the non-magnetic side also. Till now, there was no report of this, change in the spin textures, even by doping at the non-magnetic side. What has we can one of the possible causes might be because of arsenic doping, but we have observed an increment in the lattice parameter C. From the structural refinement, it has been shown as a result of arsenic doping, the D distance between the Fe1 and the Fe1 within a layer, it increases, and thereby it leads to the reduction of the exchange interaction, the magnetic interactions, which might bring in such changes even by doping at the non-magnetic side. So we have also tried to estimate the effective magnetic field that the conduction electrons can feel if it traverses through this kind of Skyrmion-like textures in the system, and it basically fills a fictitious magnetic field which gives rise to the topological Hall effect. So we have tried to estimate that using this, and the effective magnetic field that we have observed is maximum for FGT, and it gradually decreases as we have increased the non-magnetic side doping with cobalt, as well as same behavior has been observed for the non-magnetic side doping also.
Any good question?
Yes.
Yeah. So in this case, you told that point 4 arsenic. So the in plane is easy access,
Mm-hmm.
but you still see the topological Hall in this direction. Why is that? Normally, you get this topological Hall when you apply the magnetic field along the hard axis.
Mm-hmm. Achha, okay.
But in this case,
Yes,
point
yes.
4, you are getting this topological Hall in the easy direction. So why is this true?
Mhm. Yes, just I agree. But like when the magnetic field was in this direction, we could
In
not
principle,
see.
it should be in that
Yes,
hard direction,
hard
which is
direction.
still showing you a good
Anomalous
anomalous Hall.
Hall effect.
But
Yeah,
in
yeah,
this
yeah.
case, even if your magnetization saturates very easily,
Mhm,
it still gives you a topological Hall which is not saturating.
mhm.
So why?
Yeah, that's a good point. Like that is something we also thought of. Like we tried to
Because
calculate.
you can see here
Mhm,
the saturation field is very small. No?
mhm.
So it is not at all. Then it is very difficult to fit and get a topological
Topological
Hall.
Hall,
No?
yes. Because in
How do
FGT
you?
also the topological Hall is being observed only when the magnetic field is along the, perpendicular to the c-axis, along the hard direction.
In this
I
case,
totally
it's
agree. Yes, because
almost impossible to get
huh,
the value of the topological because your resistance is not following anything about this scientific behavior
uh,
from MH curve. At
from
least.
here, yes, I can understand because there is a spin reorientation kind of stuff happening. The easy direction is moving from the out of plane to the in plane direction now.
Yeah, but you are doing this at 5 Kelvin, and 5 Kelvin it is very different. Magnetization and your rest all effect that.
This one you are telling?
Yeah, point 4, it is still going up from 0 if you start.
Mm-hmm.
It should have saturated according to your magnetization.
I understand, but we could not separate the reason. We could not find out the exact reason, and because we tried to also find out the anisotropy constants and all that, because it was changing from the image curve. It appears that the the easy direction is now changing from out of plane to in plane. So I totally agree with you. Ideally, the like this behavior would have been reflected here also, right? But we are not getting that, but we couldn't find a proper reason for this. Okay, so we have estimated the effective magnetic field, and so what we can conclude from this part is that we have successfully grown high quality single crystals of Fe3GeT2, which is a van der Waals ferromagnetic material, and we have doped it with cobalt at the magnetic side and arsenic at the non-magnetic side. And the magnetization measurements reveal a reduction of the Curie temperature for both cobalt and arsenic. And the magnetotransport studies exhibit unconventional transport behavior and a non-trivial contribution to the Hall effect, and we have demonstrated a tuning of the unconventional Hall effect by chemical doping. So now I would like to come to the second part of my talk, but before moving on to that, I would like to answer your question about what might be the reason for the stabilization, of these kind of topological structures in Fe3GD2. Now, very recently, I mean, theoretical calculations, it has been shown that one of the possible reason is that a competition between the dipole-dipole interaction, the exchange interaction, and the magnetic anisotropy altogether is playing a key role in stabilization of Skarmian-like textures in the system. This is a very recent one, and which is being going on right now. And another reason or another possible reason I would like to show you, but I have to go. Yeah, this one. So if you consider the magnetic structure of the iron sublattice, okay, so when the magnetic field is applied parallel to the c-axis, which is the easy axis, so what is happening? The spins are now collinear to each other and we don't have any chirality. But when the magnetic field is applied, in the perpendicular to the c-axis or parallel to the AB plane, since c-axis is the easy axis and AB direction is the hard direction, so as we are applying the magnetic field, there is a spin flop happening. But this system also has a large magnetic anisotropy. So this competition is giving rise to a non-coplanar structure, Si.Hj cross escape term, which is giving rise to the chirality, and you have, existence of this kind of texture in this Fe3GT2 system. It's one of the
But this again contradicts your point for arsenic.
yes, like for the point for arsenic, I probably have to investigate further. But in case of FGT, these are the two possible theoretical reasons going on. One is this, another from micromagnetic simulation. People are saying that it's because of the dipole-dipole interaction exchange as well as magnetic anisotropy, which is bringing a stabilization of this kind of textures.
But in principle, if I have to look for a Skarmionic system, then anyway, I can look in any magnetic system, not to now I don't have this. BMI might not be there for me BMI. So what is the guiding principle it's becoming more
There is systemic defects.
rather than isotropy?
Anisotropy is very, very important. Very, very important.
This this paper, I think, the schematic one, so they already observed this PRT, right? They already observed this topological model. They claim, right?
Mhm.
This FGT. So you are also seeing similar behavior, but with doping.
Yes.
No, she also says
In
that
FGT also
Yeah,
and
yeah. FGT she also sees, yeah, but she also dope it and
But this paper now, the recent results that are coming up, they are kind of contradicting these also, this figure. So it's not
yeah,
because
this is
of
just a
the
schematic.
spring club. They are telling it's because of the three competitions happening. That is the actual reason behind stabilization of Scarmians in FGT. Okay. So we have also done some collaborative work where we have actually exfoliated the FGT crystals and made flecks. And there are also reports on 8382 where they have shown that below a certain, thickness, they are not observing topological Hall effect. However, from our data, we could see the thickness that we have measured is around 30 nanometer. We could still see a topological Hall effect, but that work is it's under process right now. Okay, so now I would like to move on to the second part of my talk, where I'll be talking about magnetotransport in layered antiferromagnetic systems. So the reason why we are interested in antiferromagnetic systems is it's basically because of the recent studies that have come up that people have shown that by you can electrically switch the antiferromagnetic order using both electrical and optical techniques. And the reason why this is interesting is because people are interested in controlling the controlling the antiferromagnetic order by electrical or optical ways is that the antiferromagnetic system they exhibit fast spin dynamics and also they are not affected by the stray magnetic field which gives a favorable situation. However, these are one of the recent works where this is on the first report I think antiferromagnetic system, and there are further research reports where people have observed scarmions in synthetic antiferromagnetic systems. Now, anyways, like these are not related to my work, but that's one of the motivation that why these antiferromagnetic systems are important, and also there are recent investigations, and for doing all these things, we need to have a basic understanding of the different magnetoresistive behavior in antiferromagnetic materials. And recently, people are focusing on the impact of magnetic field on the flip spin, configuration of antiferromagnetic system, the fast spin dynamics. However, generically, altering the antiferromagnetic ordering and controlling the resistance in antiferromagnets is quite of a challenge. By the magnetic field is generally difficult, which leads to weak magnetoresistive signals. And this has been reported in a series of collinear antiferromagnetic systems. However, there has not been much focus on the low dimensional layered compounds or chain-like systems until recently. One of the systems is NACRTE2, where very recently they have shown that it has been shown that under application of magnetic field they have observed a large magnetoresistance because of spin flipping in this layered antiferromagnetic compound. So this prompted us to investigate magnetotransport in some layered antiferromagnetic systems also. So with this, the system that we have studied is PAFE 1.25T3, and among the different families of the layered antiferromagnets, the iron-based chalcogenides They have always attracted attention because of their relatively high ordering temperature, the coexistence and competing relationship between magnetism and superconductivity. So we were interested in this system TAFE 1.2, T3, and it crystallizes. It has a very unique crystal structure. It crystallizes in a monoclinic structure, and if you see the building block of this is basically it forms. It is a mixed metal. It forms a. It crystallizes in monoclinic structure and comprises of a mixed metal network of tantalum Fe, and moreover there comes a second Fe2 atom, partially occupied Fe2 atom that sits in between the interstitial sites. So it has a very interesting crystal structure, and the key feature is that it is antiferromagnetic with a transition temperature of around 200 Kelvin. So we first tried to grow the TAP 1.25 T3 compound sample using the chemical vapor transport method. We tried to grow this using both kind of transport agent, both iodine and TCl4. However, with iodine, we were not being able to grow the single crystals. So this gave us good single crystals, but they were needle-like crystals. They were long enough to make contact, but they were very, very, the width was very small. So it's very difficult to make contact in this system, especially when we cleave it. And okay, so before moving on to the results, I would like to give the characterization of the single crystals. Here you can see, it has a very unique magnetic structure also. So the Fe atoms, the Fe1 atoms, it comprises of a two-leg ladder kind of structure. The Fe1 forms zigzag chains. Okay, the Fe1 now and they are ferromagnetically coupled to each other. And then the Fe2 atoms, they are also ferromagnetically coupled to the Fe1 atoms within a single ladder. However, the interladder coupling is antiferromagnetic in this system. So it has a interesting magnetic structure, and now with this will help us in understanding the magnetotransport property. First, I would like to give the characterization of the sample from the X-ray diffraction. The peaks could be identified as 1, 0, -1 peak, Bragg peak, and from the energy dispersive X-ray spectroscopy, we could confirm the concentration of iron to be 1.25. This is very, very important in this sample because the iron concentration determines the Tn. So from the Tn we observe as well as from the index we could confirm it is actually very close to 1.25. So from the magnetization results, what we have seen is that from the temperature dependence of magnetization, as we go down from room temperature, we could see a sharp transition at a temperature of around 195 Kelvin, which marks the onset of antiferromagnetic order. And the real temperature that we have observed in our sample of 195 Kelvin is slightly higher than the other reports on other single crystals of TFT, which also confirms that our iron concentration is actually close to 1.25 only, because they in most of the systems, most of the reports, it's quite lower than 200 Kelvin. But the first report was probably on a polycrystalline sample, and it reported a Tn of around 200 Kelvin. So our Tn that we have observed confirms the iron concentration to be close to 1.25.
Could you please go back to the structure? So here I can also get 1.25 if I count those iron. Iron 1 5 itself, because that should match. Right? Those are two phase center. Maybe that should match. One counts. 1.25.
It's easier to go back and see main crystal structure which you have.
So is one unique cell. But I think the other image was one unique cell. Or other image that you were showing.
There are two formula units per unit cell.
Two formula unique cell. Yeah. Okay. Maybe it is.
You have to count it.
Yeah. Yeah.
You have to recognize units and count it.
And also which location it's
Location is key. I think it's a center. For sure.
over here.
Yeah.
We
Okay.
can have it.
Yeah, I just try to show the magnetic pattern how it
Yeah, better to
like it. This iron forms. They consider it to be one ladder where the iron chain goes like this, and the Fe2 also happens ferromagnetically, and it runs along the B axis or I mean the sample surface. Because we have observed something extra also, but we are still not being able to understand this. The sample clips in this direction, the sample also gets clipped in this direction. The T, I think probably the TET,
more like one dimensional
yes,
and chain.
yes, yes. So the clipping, whatever we will be talking here is in this direction. So what we have observed when the magnetic field is applied perpendicular to this 1 0 minus 1 10 that's in the out of plane direction, the Tn is weakly suppressed. So from the field dependence of magnetization, when the magnetic field is applied in the plane, we see that M increases linearly with the applied magnetic field. This is common in case of the antiferromagnet. However, when the magnetic field is applied perpendicular to 101 in the out of plane direction, we see that for 5 Kelvin and 50 Kelvin, they almost rises, I mean increases linearly with age. However, when the temperature is close to 120 Kelvin, after a certain threshold magnetic field, there is a sudden increase of the magnetization. This as well as, this magnetization curve also hints that there exists a magnetic anisotropy in this system. Now, in order to clarify that, we have tried to study the anisotropic magnetic property, and we have measured the we have calculated the isothermal magnetic entropy change in the both the directions, and we could, if we subtract these two, we got this difference of the two isothermal magnetic entropy change, and we could see that it shows a finite, it gives a finite value, which confirms that there exists magnetic anisotropy there in this CFE system, and also we have seen that this peak position with increase of field, they are shifting towards the low temperature, which also we these one and the image curve, they hint of a possible existence of spin flux in this system. And here you can see the temperature dependence of the spin flux field, which is obtained from the image measurements when the magnetic field is applied in the out of plane direction. Now, this shows the temperature dependence of the resistivity. The geometry is this: the current is always in the plane of the applied in the plane of the sample, and what we have observed is that throughout this temperature range, we could see a metallic behavior and a change in the slope at around 195 Kelvin, which matches with the magnetization data. And another interesting thing is that when the magnetic field is applied perpendicular to this 1 0 minus 1, that's out of plane, we could see an extra kink in the data. Okay, and we probably feel that this might be because of some spin flux under this applied magnetic field of 9 Tesla. And we have the magnetic transport measurements which support this. And from the transverse for resistivity versus magnetic field,
But
here
you should see that in magnetization measurement.
mm,
Image curve
image,
or empty image.
yeah, but we
You
measured
don't
in
have any data in 90s.
no. Till 7 Tesla we could measure.
But corresponding to that temperature, there is nothing in T spring of your magnetization. There should be something.
Yeah,
If you are claiming it to be spin flop, there is more evident in magnetization.
Yeah,
data than-
especially here. Yes. So we think that might be because of the spin flop, but however,
But I think spin flop will be directly seen more in magnetization data than in transport data.
but this behavior is also an indication of the spin curve, right? Like after 120 Kelvin, when we measure the image curves, all the image curves show the tendency of increment after a certain magnetic field. So
That the transition is a very sudden. If we
Not a
see any
continuous. Basically, spin clock you see some sudden transition. Generally, yeah.
yeah, from this, if we from the image curve, we took the derivative, and from there we could see like
There
but
is
that
sudden
appeared
change.
that appeared only at 9 Tesla or
no.
that
That
that transition the next slide.
okay, yes,
Yeah,
yes,
that
it's
is only at 9 Tesla,
at 9 Tesla.
which you have not
Mhm.
applied in your
In
valorization.
valorization. Yeah.
And
Because
that's
that we confirm that it's probably because of the spin clock happening.
reproducible. Have you checked?
Yes, it is reproducible. Yes. And we have done measurements on number of crystals of the same batch as well as different batch. Yes. And why am I telling it spin flop is also because that I show as I'm increasing the temperature, the spin flop field is getting reduced. So this also it gives an indication that it's spin flop happening in the system. And okay, so from transverse resistivity versus magnetic field, here also you can see this is the Hall resistance versus magnetic field, and when the magnetic field is in the plane of the sample, for all the temperatures, you see like it basically shows a linear increment with magnetic field. Okay, however, you cannot see this because I have plotted both the directions together. But when the what is interesting is that when the magnetic field is applied in the outer plane direction, for 5 Kelvin and 10 Kelvin, rho xy or rho t, it increases with age. However, for temperature at or above 150 Kelvin here, we can see two distinct regimes are clearly evident. And one linear below a threshold magnetic field, and once we apply that threshold magnetic field, it's increasing suddenly, which might be attributed to an increment of the net magnetization because of the spin flop ordering of the antiferromagnetic moments under a magnetic field when it is applied in the out of plane direction. And not only that, in order to study this, we have also performed from the magnetoresistance versus spin data from the longitudinal magnetoresistance. We could see that I have not shown all the curves here, but what we have observed is that below 100 Kelvin, magnetoresistance with the applied magnetic field being applied in both the directions, they show similar kind of behavior. Like it gives a small negative value and it doesn't show any this kind of change. It shows this kind of a value. I mean, this kind of a behavior. Okay. But however, when the magnetic field is applied in the out of the in out of plane direction, that to above 130 Kelvin, we have observed that the MR increases and then after a certain field, it shows a sharp drop. And this threshold field corresponding to the drop, it decreases from 8.4 Tesla for 130 Kelvin to 6 Tesla for 180 Kelvin. And in order to understand the impact of the external magnetic field on the bulk antiferromagnetic ordering this TFT, it is important to understand the magnetic structure that we have shown that in case of TFT, it basically comprises of, like iron chains where the Fe1 irons, they are coupled ferromagnetically. The Fe2 atoms that are partially occupied, they are also coupled ferromagnetically within a single ladder, the intra-ladder. However, the inter-ladder coupling between the Fe and Fe, that is antiferromagnetic. So what might be happening is because of the application of magnetic field in the outer plane direction, above a certain temperature, there is a spin flop happening. Spin flop of the antiferromagnetic moments happening because of the application of the magnetic field, and you see this kind of a sharp drop here. So and also, so we now have two things in the system. One is spin flop, and also we have magnetic anisotropy. So, in order to clarify the manifestation of the anisotropic behavior, we have studied the angle dependence of the magnetoresistance in this system. So, this is the measurement geometry that we have used, and these two here you can see the transverse resistivity or the transverse fault resistivity with respect to angle phi. Now, what is phi? Phi is basically the angle between applied magnetic field H and the current I. Now, I is in the plane of the sample. Now, the H is also in the plane of the sample. So, phi is basically angle between H and I when both H and I are in the plane of the sample. So, in this configuration, what we have observed is we have seen a harmonic behavior of rho t versus phi, and the amplitude of it decreases with increasing temperature, and it decreases with decreasing magnetic field. Now, considering that it has a A-type antiferromagnetic order, TFE 1.25 kg, we have the A-type antiferromagnetic order, and absence of any spin flop configuration for H in the plane of the sample, this can be attributed to simple anisotropic magnetoresistance behavior arising from the orientation of the Neal vector with respect to the current, which is common in case of magnetic materials. However, what was striking is that when we measured the transverse Hall resistivity as a function of transverse resistivity as a function of theta. Now, what is theta? Theta is basically the angle between H and I. Now, the H is moving from in plane to out of plane direction. So, what we have observed, this one and here also, that there is a deviation from the harmonic behavior which is observed for H versus theta, and we have seen sharp changes in the rho t, and it is strongly dependent on magnetic field. However, it doesn't. It is weakly dependent on temperature. So, if we consider that, if we neglect the contribution from the spin flop configuration arising in DFT here, this anharmonic nature might be attributed to magnetic anisotropy in DFT. Okay. So now with this, we wanted to further explore, and what we have seen when we have measured the angular dependence of longitudinal resistivity rho L with respect to theta, that is when the magnetic field is rotated from in plane to the out of plane direction, it shows a striking behavior. So as you can see over here, that for 10 Kelvin, 50 and 100 Kelvin, and even for 130 Kelvin, when the applied magnetic field is around less than 6 Tesla, it's 6 Tesla, we see a harmonic behavior in delta rho L. However, when the magnetic field was increased to 8 Tesla and the temperature is also increased, equal to 130 and above 130, we could see this got modified to give this kind of a feature. So what we have observed is an anharmonic behavior. We can see a plateau-like feature happening, and at certain angles there is a certain increase in the magnitude of longitudinal resistance, or you can say a sharp drop in the longitudinal resistance. And also we can see that as we are increasing the temperature, there is a reduction in the magnitude of rho L, which can be attributed to the enhancement of the speed fluctuation near Tn. So what we have observed is this dramatic behavior. In order to understand that, we further extracted the amplitudes of the resistances that we have measured, and what we have seen is this is the amplitude of the transverse resistivity. It decreases with temperature both for theta and phi rotation, and this is expected for magnetoresistance signal originating from magnetic order. However, when we have checked this dependence, where amplitude of longitudinal resistivity versus temperature, what we have seen is for phi rotation, it decreases monotonically. However, for theta rotation, up to 10 Kelvin, both of them matches. But in a temperature window of 130 to 150 Kelvin, for theta theta rotation, there is a sudden increment in this delta rho L. So considering, in BFP, if considering the A-type antiferromagnetic ground state with intra-layer ferromagnetic alignment for phi rotation, the applied magnetic field is perpendicular to the nil vector, which is roughly oriented at an 18° with respect to the surface normal. So what is happening? No further reorientation of the nil vector under phi rotation is occurring, which results in a monotonic decrease of the magnetoresistance. However, if we look into this picture, for theta rotation, that results in the magnetic field rotating between the magnetically easy and the hard directions, and that brings in profound effect on the antiferromagnetic moments. So and we have seen there is a sharp drop in rho L when the H is in the out of plane direction that is applied along the magnetically easy direction in case of the MR data also. So there is a significant enhancement in delta rho L, and this can be attributed to stabilization of spin top configuration of the interlayered antiferromagnetic configuration, as well as the study also indicates that there exists a strong interlayer magnetic coupling in this system. So I would like to conclude that we have grown needle-like single crystals of TFE 1.2, TFE 1.25 T3, which is a layered antiferromagnetic system. Temperature and applied magnetic field dependent magnetization measurements reveal existence of an anisotropic behavior when the applied magnetic field is applied in the out of plane direction of the sample of the crystal. It resulted in a spin clock-like transition at around T equal and above 130 Kelvin, as opposed to the antiferromagnetic nature when the magnetic field is in the plane of the sample. So this spin clock behavior, it also manifests in anisotropic magnetotransport behavior, and it results in a sharp drop of the longitudinal resistivity at similar T and H configurations. Angle-dependent longitudinal magnetoresistance around the spin clock transition shows a strong anharmonic behavior along with a pronounced enhancement in its magnitude. So what we need is basically future experimental investigations concerning modification of this unusual longitudinal MR around the spin clock transition with the variation of the number of layers, because we are seeing the interlayer coupling is also playing a role. So it is important to perform the experiment by changing the number of layers, and we can possibly look out for any existence of non-trivial configurations in this system, which might initiate a new shift of in the field of antiferromagnetic spintronics with layered material systems. So I would like to thank my host at IISER Bhopal, Dr. Ravi Prakash Singh, and my collaborators from Dept University and SIMP. These are some other systems on which I am currently working on, and I'm also working on in collaboration. Apart from this MOOC, I'm more focused right now on fabricating, exfoliating the van der Waals systems using dry transfer technique and proving the transport properties. And thank you for your kind attention.
For a nice talk. It's now open for questions. So there were a lot during the talk. Then, oh yes, okay.
So in all this interpreting, you have taken a rho XX square. So any special reasons to taking this term? Or you can just take rho XX. Why you have taken rho XX square?
Okay. As per right now, as per as I can remember, the anomalous Hall contribution is basically RH and it's MZ, right? That part corresponds to the anomalous Hall contribution, right?
Yeah.
So within that RH, you basically have, I think it's coming from the tensor. I cannot recall it right now, but if you can just check now the RH contribution to the RH. You can write rho xy equals to RH mz plus the ordinary Hall contribution. So if you look into to carefully that RH actually has got contribution from rho x6 square.
No, I think rho x square you are taking, assuming that everything is intrinsic.
Intrinsic. Intrinsic
Huh,
is
that
one.
is true. That
So,
is
but,
true.
but why is that assumption? How do you know it's intrinsic? Could be from skew scattering and.
No. Okay. Like, okay. We have checked that also. From the conductivity, we have calculated the sigma xy, and we have shown that the range it is coming is because of the intrinsic contribution only. We have checked that. Yes, we have done that. I should have shown it, but yeah, we have done confirmed it.
One small question. What are your Fe1, Fe1 distances in the last compound? Fe1, Fe1, Fe2, Fe2, and Fe1, Fe2. And are they all similar or
No, they are not.
how?
This intraladder Fe1, they are around 2.7 angstrom or something, but they are the value is smaller. Okay, but both in between Fe1 and Fe1 Fe2. However, the interlayer distance between the Fe1 and the Fe1 is around 6.
But I guess it's all through tellurium network.
Probably, but
Exchange coupling might
yes.
be. If there are no further questions, we thank Rajeshwari again.